Hello, today we are in the area of process control systems and specifically looking into user interfaces for these systems. And I'm going to present a method to generate user interfaces for such control systems. You see already the operator workplace in this title picture, and here's a magnified view of that. And plant operators use these kind of user interfaces to supervise and monitor a production plant. They have visualizations of tanks, motors, valves, and pumps. They can read live sensor data from these displays, and they see the connections between the different elements, and they can also interact with actuators like motors and valves and run the entire processes. However, an operator does not only see 6 screens like on this photo here, but in actually a medium-sized process production plant can have hundreds, even thousands of operator process graphics. So the problem is, if now an alarm occurs in some area of the plant and the operator is currently in some other area and visualizing that, then an operator needs to track down the root causes and move through a lot of navigation steps through a lot of different displays, switching them on different screens, and then actually coming to the root cause, which might be a sensor malfunction or some leakage in some pipe. And this navigation takes a lot of time. It's error prone, it's quite a heavy cognitive process, and that's why we want to improve that. One concept that is already available are zooming user interfaces. They have been in research for over 60 years, starting with Sketchpad and then Pad++, and Google Earth was a commercial product released in 2001, and also the iPhone has a zooming user interface as the main user interface. Google Maps uses this heavily, so you can zoom seamlessly between different levels, and then the level of detail is also dynamically adjusted depending on your zoom level. And this allows you even to visualize very large maps and to do some route planning in very complex topologies. At ABB, we also have a prototype for a zooming process graphics, which dynamically adapts the level of detail depending on the zoom level. This was built already 10 years ago as a mock-up tool, as a visual demonstrator. However, the problem was that these process graphics had to be manually engineered by hand, so on different zoom levels. So we had extra engineering efforts. It was completely detached from our existing process graphics, so it's very difficult to retrofit existing plants. And back then it had also limited perceived utility. Now our idea is here to take this idea and take it further and say, okay, we want to generate those graphics based either on piping and instrumentation diagrams or even existing process graphics, do an automatic generation step, and then come up with this zoomable process graphics on multiple different zoom levels, which the operator can move between and switch between, can pan and zoom, and then much more easily browse the topology and find root causes for any kind of alarms or issues that arise. There's also some related work on HMI generation from the Technical University of Dresden, the auto HMI approach, and then there was an approach for module type packages generating user interfaces from that specification. And we have some own related work where we, in former work, generated process graphics based on P&I diagrams. However, that work did not end up in a zooming user interface, but rather in traditional user interfaces. And the same issue also applies to the other related work. None of the other related work has ever attempted to generate zooming process graphics. Good. Our method that we propose here in our paper has 5 steps. First, we start with PNIDs and process graphics. We have a source importer that translates those notations into an object-oriented topology model, which contains elements like motors, pumps, tanks, pipes, and so on. And from this notation, together with the graphical coordinates that we have from existing process graphics or process and instrumentation diagrams, we can generate graphics. This goes almost automatically. We end up in process graphics. Then we have a graphics layouter that can arrange the different screens besides each other. And then we end up with layouted process graphics. And then finally, we can also configure the level of detail that is displayed on different zoom levels. And then we end up with zoomable process graphics. And this is the output of our method, which is actually then used by a plant operator through a graphics navigator interface. We also implemented the method in a prototypical software tool based on .NET. So it's a desktop application, and you see here you can display a process graphics inside this notation. These graphics are generated. We have live sensor values displayed. We have navigation buttons to move between different screens seamlessly. There's a minimap to visualize the entire topology in a small area to very fastly switch between screens. We have an adaptive level of detail zooming, which I will show you in a minute. We have custom page layouts. We have a search interface where you can search for elements in the graphics, which are then highlighted. And all of this gives us then this new HMI generator. Let's run a short demo, and I skipped this step of importing the PNIDs, which you can read up on the paper, and we directly move into the graphics generation. Let me run this for you. We see here a PNI diagram, which we imported into our tooling, and now we can overlay that with actual graphics generation. First, we do some simple colorful shapes, but now we also use shapes from a process graphics library. If you eliminate the background here, you see the actually generated graphics, and then we can also integrate labels from tag names. Then we overlay this with live sensor values using OPC UA clients. And then we can also show the navigation across different screens here. So you can zoom out from the process graphics and then display multiple graphics at once. You see already here some detail is omitted. You can zoom in then again, more detail is visible. We have generated some connector buttons from the page connectors that we found in PNIDs. And this allows you also to very fastly move between the screens, but still keep some knowledge on the arrangement of everything. There are different layouts, how you can arrange the screens. For example, here we see a hierarchical top-down layout with an orthogonal edge routing. An organic layout, which is displayed here, arranges the screens very densely. So if you have to move quickly between different screens. And then there's also a circular layout, which is very helpful if you have many interconnections between different nodes and really have to understand those interconnections. But it's also possible to do a manual layout of the graphics, depending on how those diagrams and graphics had been laid out initially. And therefore, we have here this manual layout editing, where we can then arrange the screens as preferred by an operator. And then we see an arrangement that makes most sense, and in many situations the best usage for the operator. Okay, now we look a little bit at the level of detail configurator. You see on this highest abstraction level, some pipes and instruments have been actually removed so that only the high-level topology is visible, and which allows an easier navigation. And as we zoom in, more elements become visible, and this is done algorithmically. So it's done on procedures that we have programmed. It's not pre-programmed in a sense that we have modeled each different zoom level individually. And we can also zoom in, and the fonts are scaled dynamically so that they are always well readable on the screen and do not waste too much screen space. And this kind of level of detail zooming could be also extended and be made more sophisticated in future work. That's it for our demo, and then let's look at the case studies that we have performed. So we had two case studies. One was we generated the zooming process graphics from existing process graphics from an ABB process control system for an oil production facility. And we had as input 93 different diagrams, and you see here we imported them into our graphics generator, and it ended up in more than 5,000 nodes and almost 2,000 edges. The graphics generation in this case was quite fast, like 2 minutes for the entire generation, and most of the stuff could be done procedurally. So this showed us a little bit the scalability of the approach. And then in a second case study, we looked more at the density and the level of detail that we could achieve. This is also the case study that you saw on the demo. This was based on a chemical plant. It was generated from smart PNIDs, and here we generated 2,600 nodes and had 255 edges. Generation was quite fast because it was only 9 different screens, so only 10 seconds were spent on generating the graphics. This showed us also that we can have this very high level of detail based on smart PNIDs. Then we also did, for evaluation purposes, a cost comparison. So we estimated the costs for doing a manual engineering of the graphics and doing our automated generation. And you see different tables here. So this table is about the traditional manual approach, and this table is about the automated approach that we have proposed. And here you see the cost savings. A lot of assumptions go into these calculations, which we have spelled out in the paper. For most of them, we have references based on public sources, for example, for the work hours spent per graphics and so on. So this is all detailed in the paper. You can read it up. But if we sum everything up and we assume a plant that needs 1,000 diagrams, then the manual approach in our estimation takes approximately 8,000 working hours to be completed, while with our automated approach, which is basically mostly based on procedural generation with a little bit of manual reworking, we would estimate would take 2,000 hours. So we around 2,000 hours. So we estimate a cost savings potential of 74%, at least for the cases that we have considered here. To conclude, we have generated HawkEye HMIs. These HawkEye HMIs can enable finding root causes up to 90% faster. This was shown in a separate paper presented last year at the ETFA conference. They support avoiding the operator keyhole effect, so that the operator only focuses on a very specific screen area and gets lost in the navigation through the entire plant. We extend this here with an approach for generating those graphics, which requires then much less engineering efforts due to the procedural generation of the graphics. It can save more than 70% of HMI engineering costs. And because we can also import existing process graphics, this approach can be also used to retrofit existing plants and to have the zooming user interfaces as an add-on to an existing plant. In the future, we plan to improve the visual quality of the generation, to improve the auto layouting, so that we have less visual clutter in the diagrams. And then we also want to perform a lot of usability tests with plant operators and refine the visualizations based on them. There could be also some algorithmic optimizations of the visualization by, for example, eliminating those page connectors and then directly drawing the piping lines between the different elements. That's what we are still working on. Thank you for your attention.